Oh, did you?
Get confused. And then just don't get confused. It's not. No. My main concern is when I get to the okay. Okay, hi, good afternoon, everybody, and welcome to the online audience as well. Today we have Rachel Mey going to give us a talk about something a little bit different to what we normally hear about environmental geochemistry. So Rachel joined us in June, and she joined us in the IGF labs downstairs. Very from careful attention to detail, and she's been very supportive of all the students that have been coming through the lab and helping with their research and their analytical work. So we wanted to support her back and hear about all the research that she's been doing. So she did her master's in the School of Chemistry with Rachel Mey in my country. And she'll be telling us a little bit about all her different research experience, and then she's going to get into the research that she did. Oh, thank you, Rachel. Thank you, Cara. Thank you for everyone coming. I'm really terrified that you're all here, but I hope that you enjoy at least one thing about what I say. So yeah, Karen introduced it pretty well. I'm going to be speaking about my different research interests and touching a little bit on my master's. Okay. So I did my undergraduate degree in chemistry with chemical engineering here at Wits. I decided I was quite interested in environmental chemistry, so I decided to continue with my honors in chemistry. We did 2 projects in chemistry. My first one was crystallography, where I focused on enantiomorphism in sodium chlorate. And then in the second semester, I did a geochemistry project with Mark Humphreys, where we were looking at paleoclimate reconstruction. That we'll touch on a bit more later. After my honors, I worked for Anglo American Platinum. I worked at the Rustenburg base metal refinery. I was monitoring the water quality of their boiler water and wastewater using a few different techniques, such as pH, alkalinity, hardness, chlorides, trace metals. We did a whole lot of titrations and used ITP OES. After about 8 months, I decided I was really interested in paleoclimate and wanted to come back to Wits. So the reason we care so much about paleoclimate is understanding past climate can help us predict future climate scenarios. This is particularly important in South Africa, where climate change is a pressing issue. We use different proxies or indirect measures of paleoclimate from various archives. So one of the archives we use are tree rings. Tree rings help us infer changes in precipitation, in temperature, and drought conditions. Speleothems, we can use the stalagmites and stalactites to infer changes in precipitation and humidity conditions. This is a nice one I found at the Pango Caves earlier this year.
A nice South African example is hyrax middens, where we use dusty middens to infer changes in vegetation. So their middens capture pollen and phytoliths quite nicely, where we can infer changes in vegetation, which we can use to infer changes in precipitation, in temperature, and a whole lot of climate conditions. And what I'm really interested in is cores. Cores have a natural accumulation of sediments as we go. So older sediments are at the bottom and younger sediments are at the top. This provides a nice continuous record of climate changes. We also have ice cores, which capture signals for atmospheric change, and coral cores, where the growth bands reflect changes in ocean temperatures and salinity. So we use paleoproxies from all these different archives to infer different climate conditions. We have a few different proxy categories. The two I'll focus on are chemical and biological, where chemical ones help us infer changes in temperature, hydrology, and atmospheric conditions, while organic molecules like fossil pollen and phytoliths help us infer temperature changes through vegetation, and diatoms and forams help us infer marine changes. Just going to take a sip of water before I start speaking about my master's. So in my master's, I was looking at climate change during the Lake Quaternary in the Southern Cape Coast. The Southern Cape Coast has quite a complex climate with important atmospheric and oceanic systems affecting the climate. There's been significant climate change in the Southern Cape Coast, and we don't have a great understanding of the different forcing mechanisms behind those changes. The reason we want to understand those climate changes is the Lake Quaternary provides the closest modern day analog to climate changes. So by understanding the forcing mechanisms, we can develop better climate models, understand future climate change scenarios, and prepare for those. Like I said before, this is important because in South Africa, water scarcity is already a pressing issue. And we have a lot of important biological zones that we want to protect. So I wanted to reconstruct the paleoclimate conditions in the Southern Cape Coast. And these are the different proxies I used to do that. So Pearly Beach is a little coastal town. My study site is there. It's situated on the Greater Argyle Plain, which stretches from Science to Strathspey. So here is our study wetland. It's a coastal wetland. It's about 30,000 meters squared, and it's got an average water depth of about 1 meter. Its closest town is Pearly Beach, about 2 kilometers away, and it's about 650 meters from the nearest shoreline. It's got a vegetated coastal dune shielding it from the coast, and it's fed by the Holcall River. It only flows to the ocean during really wet seasons, otherwise it's closed off to the ocean. So I'm not sure how everyone's background is on climate, so I'm going to go a little bit into that. The South Africa can be divided into 3 main rainfall zones. The winter rainfall zone, which receives most of its rainfall, 60%, during the austral winter months. The summer rainfall zone, which receives 60% of its rainfall during summer months. And there's a small zone in between, which receives yearfall rain. The rain in the winter rainfall zone comes across through cold fronts, which is driven by the westerly winds. Another important atmospheric forcing mechanism is the South Atlantic anticyclone, which pushes cool, dry air to the coast. The Benguela current flows by the Southern Cape Coast. It is a cold ocean current. And we've got the warm Algalus current as well. During the summer months, upwelling of the Benguela is its strongest, which prevents moisture from reaching the study site. During the winter months, the Benguela current weakens and the South Atlantic anticyclone shifts north. This allows the westerlies to increase their influence on the winter rainfall zone, which brings across all the rain in winter. This is enhanced by increased moisture from the Algalus current, which is why during the winter months we have increased rain and it's really cold. An important paleo-forcing mechanism is the Atlantic Meridional Ocean Circulation, AMOC. The AMOC takes warm water in the south and transports it to the northern hemisphere. When AMOC conditions are stronger, there's a net cooler in the southern hemisphere because more warm water is being pushed northwards. When AMOC conditions are weaker, there's a buildup of heat in the southern hemisphere, which increased moisture uptake in the region during that time. So the first part of our project was to sample the core. It was retrieved using an GEOTAK piston coring system in November 2021. And it was then taken to the Nelson Mandela Paleoecology Lab to be split and subsampled. We used a few different methods. We developed an age model at Queen's University using radiocarbon dating. Organic carbon isotopes was collected at Stellenbosch University. Inorganic elemental analysis was done on an XRF. Mineralogy was done on an XRD, and grain size on a Melbourne master sizer. So our age model is presented here. We collected 8 bulk samples presented by the little red stars along the core. The deepest sample was just under 5.5 meters and dated about 30,000 years. The most recent sample was about 10 centimeters and dated to 1,000 years. So now to some of the results. Relative sea level influences the wetland by controlling the base level of the wetland. During the last glacial maximum, so interglacial period, relative sea level was quite low. This meant that water input into the wetland was restricted to upper catchment fluvial runoff from the Halfwell River. From about 11,000 years, the sea level started rising, which would have increased the base level of the river and increased fluvial deposit into the wetland. We're looking at that period here. The sea levels were rising. During this period, there's a corresponding increase in loss of organic matter. If the wetland is wetter, organic matter is better preserved, and there was also probably more plant growth in the region. So we have an increase in organic matter. The calcium-aluminium ratio can be used to infer marine changes. Calcium precipitates as calcium carbonate, which is mostly from shelf. So an increase in marine influence is seen during this period, which corresponds to the increase in sea levels. During the Holocene period, you can see quite a distinct shift to marine influence, which means marine influence overlaid any climatic imprints in the wetland. We're interested in what happened for that. So at the bottom here, I've got my mean grain size. The results revealed that the core was predominantly composed of silts and sand, with distinct increases of grain size during this period here. So grain size can be used to infer transport energy into the wetland, where increased transport energy would result in the deposition of larger grain sizes. So during this period here, we can see an increase in transport energy. So sediment sources and transport mechanisms can be inferred by using the silicon-aluminium ratio, where silicon is predominantly in sediments as quartz, which is coarser grain materials, whereas aluminium is finer grain materials or clay. So during increased energy times, more silica is deposited, whereas where lower energy periods, more fluvial input, which would be finer grain materials. So during the period of increased transport energy here, we see increases in silica content, which we can use to infer increased aeolian deposition. So there were higher energy conditions and windier conditions during this time. Titanium and zirconium are present as heavy minerals in wetlands. These are associated with coarser grain sizes. So you can see quite a clear correspondence between these peaks here and these peaks here. These heavy minerals can be used to infer grain size as well, where during high energy conditions, more deposition of these heavy minerals will occur. So this further shows increased transport energy during this period. So to summarize, during the interglacial period, we have really intense transport energy conditions and windy conditions. So what does this mean for the Southern Cape Coast? So we're mainly looking at the interglacial period here. At our beach, at our wetland, we've inferred winds and storms from the increased transport energy. PB1 is a nearby wetland where they used pollen to infer temperature changes and vegetation changes. Increases in coastal thicket were used to infer increased precipitation. We can see a correlation of increased precipitation during the periods of increased storms. The authors attributed this to a slowdown of AMOC conditions, which, if you can remember a few slides ago, was increased moisture in the southern hemisphere. So weaker AMOC conditions resulted in a net heating of the ocean at the Southern Cape Coast, which increased moisture at that time. This is also seen in the Benguela sea surface temperatures, where sea surface temperatures were increasing as AMOC was weakening. So during this time, we have increased winds, increased moisture, increased storms, which we're using to infer increased influence of the westerlies during the interglacial period. It's worth noting that it's not just a small influence. You can see here that there's barely anything during this period. So comparatively, there was quite a distinct change during the interglacial. So what does this mean for South Africa? So I compared for a few different sites from a few different rainfall zones. So we've got Pearly Beach in the winter rainfall zone. We've got Kango Caves in the year-round rainfall zone, sorry. And then Mfabeni and Cold Air Caves in the summer zone. So in the winter rainfall zone, we said that there's winds and storms driven by the westerlies. At all three of these sites here, we can see a decrease in temperatures, quite clear at the Mfabeni site. The temperatures across the whole of South Africa were decreasing during this period, not just at the winter rainfall zone. It stretches, Mfabeni is all the way at the east coast of South Africa. This is different to what the rest of the world was experiencing, where global temperatures were increasing from the beginning of the last interglacial transition. So from 20,000 years or 18,000 years, temperatures were increasing, whereas in South Africa, they were all decreasing. We're hypothesizing that this lag in temperature increase in South Africa was driven by the increase in westerly intensities due to the slowdown of AMOC conditions. This is particularly important today, where scientists are saying that AMOC is nearing the reach of a slowdown again. So we can use this information to infer that if AMOC is slowing down so drastically, we can expect increases in precipitation and decreases in temperature. And at this point, I'm just going to take a bit of water before we go on to some other research I'm interested in. So during my master's, I was involved in some ecotoxicology work at the School of Chemistry in the EnviroGeochem lab. Ecotoxicology is the study of how toxic chemicals influence different organisms and environments. We looked at a few different contaminants, such as heavy metals, which come from a wide variety of different sources, pesticides from agricultural industry, phthalates or microplastics, and PFAS chemicals or forever chemicals. Those are from different textile industries. These chemicals or contaminants enter ecosystems through seepage, and they enter all the different organisms through ingestion, inhalation, or dermal absorption. So we can use different species as biomonitoring species to assess the contaminant levels in all the various environments. By using the exposure of these different organisms to all the different contaminants, we can infer changes in the ecosystems that they reside in. The health impacts of the different organisms are varied and all obviously very negative. A few studies done by Mark in the crocodiles show that lead poisoning is really affecting the crocodiles in the St. Lucia site, as well as the trace metal accumulation in eggs. So I was involved in some mamba and crocodile studies. The mambas are quite a novel species that we're using as a bioindicator. We can use them to look at the toxin transfer within food chains. Mambas eat rats, which accumulate a whole lot of contaminants from urban regions. So we can see how those are affecting the mambas within the KZN region. The crocodiles in St. Lucia are another important one that we're also looking at. So the first step is sampling. And it's quite important to sample different parts of the animal because different parts contain different contaminants. So OCPs usually occur in fatty tissues, while as heavy metals have an affinity towards keratin. So that's nails, hair, scales. And mercury binds strongly to blood. Blood samples can show mercury, as well as liver and kidneys, which can show copper and zinc. We would then digest the tissue samples and analyze them on ICP. Another project we worked on was corals. These could show land to sea contamination, how all the toxins are going from the terrestrial environments into the sea. Corals act as sinks to these contaminants and just absorb everything that's going into the ocean. So these disrupt the reef health and cause a loss of biodiversity. So the project that collected these is the Deep Sea Connection Project. They sampled corals from 200 meters deep using drones. Here's a few pictures of that process. We then collected the corals, we subsampled them and freeze-dried them. And we extracted the contaminants of interest. We then did a few different types of analyses, GCMS for pesticides, UHPLC for phthalates, and ICP-MS for metals. In the beginning of this year, I was looking at a whole lot of different proxies in paleoclimate. I did some pollen training where we can use pollen to understand changes in vegetation, precipitation, and temperature. We also looked at phytoliths, which are silica bodies in plants. They preserve quite well, and those can also be used to infer precipitation and vegetation change. And then I also did some diatom training. Diatoms are little algae, which are quite sensitive to pH and salinity, so they can be used to infer different water conditions. And that's where I am today. I'm the research assistant in the School of Geosciences. I'm being exposed to a whole lot of different techniques, including the laser, sapphire, TIMS, and a lot of chromatography and the wiggle. I'm really looking forward to using everything that I'm learning now in my PhD. So my PhD, I want to focus on isotope and environmental geochemistry in wetlands. I want to look at long-term development and the response to climate, as well as anthropogenic factors. And I'll do this by using a whole lot of different methods: XRF analysis, organic isotope analysis, sediment source tracing, and radiometric dating. And that went a little bit too fast, and I'm sorry for that, but I have a lot of people to thank. So thank you to everyone who has supported me and funded me and helped with all the different parts of my research. Thanks.
Thank you very much, Rachel. So do we have any questions from the room before we go to the online audience? Second year? No. Go ahead.
Okay, nice presentation, by the way. My question is, using all the data that you collect, for example, ice cores, like the drill cores within the ocean floor, can we use the data from like studies like those ones? Like, can we use the data to predict future climates? Because I feel like what I heard so far is that we only study them to check to see how was the climate back like millions of years ago or something like that. So can we use like such data to predict future climate conditions? That's my question.
Yeah, so that's one of the main points of studying paleoclimate conditions. In order for us to have accurate climate models for future climate change, we need to understand the forcing mechanisms behind climate change. So why is it getting colder? Why is it getting rainier? To do that, we study past climates. We look at it got rainier, but why? And to do that, using the data from past climates, future climate prediction models are made. That's done already. People use past climates to predict future climate changes so that we can understand what might come and prepare for that.
I have a question. Actually, Grant, go first.
Thank you, Rachel. That was really interesting and very different to what we normally hear. The question that I was going to ask is about the ocean circulation variation over time. Is it AMOC or EMOC? AMOC. What causes that to change? Because it seems to have very big effects. What is the mechanism that changes the strength? Not fast enough for that.
So the last slowdown of AMOC conditions during HS1, which is during the period that I was looking at now, was due to an influx of sea ice. So that was the reason that AMOC came to a near shutdown. So, yeah.
So is that happening again now? Is that why people are predicting it?
Yeah.
Shutting down again.
I assume. But yeah, increased ice in the ocean is what led to the near shutdown during HS1.
Any other questions before I take one? Yeah, so I just wanted to ask if you could explain for the students that use the isotope labs. I think we're all used to using, or they're all used to using isotopes to study economic deposits, to understand how a mineral deposit forms and also the age of a mineral deposit. But you're going to, for your PhD, you're going to be using isotopes for something else. Perhaps you could just explain how strontium and neodymium isotopes are going to be very useful for your PhD research, just so that the students can understand a different application.
I'm just testing if I know what. Strontium and neodymium can be used as sediment source tracing. So their isotopic ratios depend on where they came from. So we can, by analyzing the sediment in a wetland, we can understand where it initially came from and was deposited into the wetland.
Strontium and neodymium. Why not like lead or hafnium or any of the range of other isotopes that we analyze?
Once I've started my PhD, I'll answer. I don't.
Okay, cool. Well, if there's no further questions, you guys know where to find Rachel. We lock her in the basement downstairs. So you can come find her in the labs, either in the mass spec lab or in the clean lab. If you want to chat a little bit more about the type of research that she does and the application of isotopic research to something a little bit different to what we do in this department. Cool. Thank you, Rachel.